Okay, so let's try to finish up here 5.2's notes on log functions here. Common log. Okay, sometimes it just says log of a number. Alright, common log is just saying, hey, if I don't tell you what that base number is, the base number is 10. Okay? That's supposedly what the common log is. So if I give you something and I don't have a little base number there, the base number is 10. That's very important to remember. And that's only when x is greater than or equal to 0. So basically there is no base. The base is 10 is what you need to remember.
Chlorophyll? More like borophyll.
So taking a look here, the natural log and e are opposites of each other. Log of e is the natural log. So that's something else to keep in mind. So this is like saying, hey, what's the base? The base is base 10. So solving this without a calculator, well, I guess you're going to need a calculator either way, but if you were to rewrite this, that's a 10 there. So that means you would take this to a 10 and you take that to the 10. So those would cancel out. So really what I'm saying is 10 to the 1.7959, which is 62.503. This, to get rid of an e, the opposite of e's is natural log. Now this, you can just give me the answer. No problem. But this is just to show you that, hey, if you had the natural log of something, if you took that to the e, like we did this, right? The base I said was 10, so I just put a giant 10 underneath it and it bumped it right up. Well, here, if you're looking at a natural log, you just put a giant e underneath each thing. E and natural log cancel out, and e to the 4.7 will give you your answer of 109.95.
Great googly moogly.
So, common and natural log properties. Remember that it's a common log, so it's 10 to the z equals x. That's 10, so that'd be 10 to the y plus 3 equals 7. Or sorry, equals z. Natural log, you take those each to the e, so it'd be e to the z equals x. And this would be e, so it'd be e to the y plus 3 equals z. So on a Richter scale, the magnitude R of an earthquake of intensity is given by this equation right here. So where I sub 0, which is this, is the minimum intensity. Okay. If I equals 1000 I sub 0, find R. So basically I'm going to take this and plug it in there. Okay, no problem. Then we realize that the I sub zeros can cancel out, so really I'm looking at log of 1000, which is like saying, hey, do log 1000 on your calculator divided by log 10, and you end up getting the Richter scale of 3 as your answer. So now it says express I right here in terms of R and I sub 0. So in order to do that, I realize, remember that's a base 10, so to get rid of this I do a giant 10, so it'd be 10R and the log cancels out. And to get I by itself, I multiply by I sub 0 on both sides. So I get I sub 0 times 10 to the R equals I.
Think of the fun you'll have taking Barbie and Ken on dates.
Example 14. Newton's law of cooling states that the rate at which an object cools is directly proportional to the difference in temperature between the object and its surrounding medium. Newton's law can be used to show that under certain conditions the temperature T in Celsius of an object at T hours is given by this. Okay. Express T, the little t, as a function of big T. That means get little t by itself. So in order to do that, you can't use natural logs here until you get e all by itself. So I'm going to divide both sides by 75. So when I do that, I now have big T over 75 equals e to the negative 2t. E and natural log are opposite, so what that basically means is I put a natural log out in front of here and a natural log out in front of here. When I do that, the natural log and e disappear on this side, and I'm left with a negative 2t over there, and the natural log of big T over 75. To get little t by itself, I divide both sides by a negative 2, And there is little t all by itself. So if I was given the big T, which was the temperature, if I was given the temperature, I could figure out how long it took to get there. And just to get rid of that, I'd probably just say multiply it by negative a half.
Here, my mystery days.
Assume that a population is growing continuously at a rate of 4% per year, approximate the amount of time it takes for the population to double in size. So, you gotta remember this formula from before. We don't know the initial population, but what we're saying is we know that the end result's going to double. So think about it like this. If the population was 100, it would end at 200. The population was 1,000, it end at 2,000. The population was 50, it end at 100. Okay, so the point is it's going to double. So when you take those two numbers and divide them, you're always going to get the number 2 as your final answer, because that's what it means by doubling. Okay, so even if I didn't have that number in there, the point I'm getting at is you're always going to end up with it equaling 2 because it's doubling. Doesn't matter what number you put in there. So really you're looking at e to the 0.04t equals 2 because it's doubling. And you could have put in any fake number you wanted to in there. It would always equal out to be 2 as long as it was doubled. So to get rid of an e, do the natural log of both sides. So those cancel out, so you get 0.04t equals the natural log of 2. And I would divide by 0.04 on both sides to get 17.32 years is how long it would take to double in size.
Good morning, Vietnam!
Alright, so I know that was a lot to soak in on logs for one section. We have the examples to go over as well. And if you're in my class, we're going to have tons and tons of worksheets and different problems to go over, so you guys will definitely get this. If you're looking at this online, you're going to need some extra problems to do in front of you. What I recommend is to go through this really slow again and try some of the examples out and see what answers you get, especially in the examples that I have. If you look up my example PowerPoint here for 5.2, try the example first, pause it, and then see if you got the answer that I got. If you have any other questions, please feel free to email me. Talk to you later.